Hello everybody and welcome back to day number 2 of chapter 4. Today we're going to continue to build on our idea of slope triangles based off of what was produced in yesterday's classwork. So as a warm-up problem for today, what I would want us to do is to draw in slope triangles and calculate the slope ratios for each of these lines. And before we get that started, as a reminder, as we've covered many times, we know that slope is equivalent to the change in y over the change in x, or you might also hear it referred to as rise over run. And that kind of was our basis for how we built these slope triangles, in addition to looking at some other aspects of right triangles. So let's take a moment and do that, and then we'll come back and see how we did. Alright, some clarity for the directions, if you haven't done so already. When it says to draw in a slope triangle, what they're looking for you to do is to draw in a triangle like this, where the end of the triangles where it meets with the hypotenuse of the line, if you will, you're going to draw those in so they go through nice points where the grid lines intersect. Okay, you don't want to be drawing a random triangle that goes from here to here because we can't really calculate the coordinates of it. So drawing in a slope triangle is one that goes through nice points on the line. So I did this in this first problem. I drew a slope triangle that went from here to here through those nice points, and so then I calculated the slope ratio, which is the ratio of the change in y over the change in x, which in that small triangle was 4 over 1, which is 4. So the slope of that line, or the slope ratio, is 4 over 1. And that's equivalent to drawing another larger triangle. I went in this blue triangle, I went over 2 and I went up 8 units to get to that nice intersection point of the lattice points. And that ratio, that slope ratio, is 8 over 2, which is also 4, which is what we should get. We should get the same slope ratio regardless of the size of triangle that we have. Because remember, those triangles we said yesterday were similar to one another, and the slope ratios of any size of the triangles for one given line should be the same. And so on problem number 2, hopefully you also got that the slope ratio for each of these was 1. And so regardless of how the triangle was, we knew that the slope ratio of 3 over 3 and 2 over 2 is equivalent to 1. And yesterday we said, hey, if we know that this has the exact same side lengths, the vertical and the horizontal component of a triangle, we also know that these angles in here, what we established yesterday, are 45-degree angles. And that's going to come into play here in a little bit. But yeah, just a little insight into what we did yesterday. So yesterday we looked at 4.1.1, and we discussed this big word, and I mentioned it a couple times, called trigonometry, which is the study of the measure of triangles. And as we move more and more into right triangles today, we're going to talk about how important the angle is within your right triangle. And so in problem 4-12, it says, what do you know about this triangle? To what other triangles does it relate? And use any information you have to solve for x. So right now we can't use the Pythagorean theorem because we only have 2 side lengths, and so a squared plus b squared equals c squared will not suffice to be able to use as a method. So what we're going to do yesterday is we're going to recognize the fact that when we were dealing with this 11-degree angle, we said that there was a ratio, or a slope ratio, that took place with an 11-degree angle, and we said that that slope ratio was 1 over 5. And so understanding that the slope ratio of an 11-degree angle is 1 over 5 for a right triangle, we can set up a proportion, because any triangle that has an 11-degree angle is going to be similar to this one. So the ratio of 1 over 5 is going to be the exact same thing as the change in y over the change in x in this triangle, and the change in y in this instance is this vertical component, which I'm going to call x. So that's going to be x over 20. And so I know that these have to be equivalent to one another. So if I solve for x, what I'm going to do then is I'm going to cross multiply, and I'm going to end up getting 5x equals 20. And I'm going to divide both sides by 5, and I'm going to find that x equals 4. So using this specific instance, we know that any triangle that has an 11-degree angle there is going to have a slope ratio of 1/5, and that was a fact that we established yesterday, and therefore I can set up a proportion with any triangle with an 11-degree angle using that same ratio and solve for x. Now, moving on to 413, I would encourage you to draw this on your paper if you haven't done so already. But what we're going to do is we're going to go again off of some of the information that we established yesterday. We said that if we have a slope angle of 11 degrees, that the ratio of the change in y over the change in x, that slope ratio was 1/5. Another thing that we established yesterday was that if we had a 22-degree angle, that slope ratio was 2/5. And the last component that we did yesterday and I hit on in the warm-up was that if we have a 45-degree angle, we know that the slope ratio is 1. And so that was an isosceles triangle. So as I look at these triangles here, and something that you should draw on your own paper, we're going to try and determine missing side lengths. So as I look at letter A, for example, this is a 22-degree angle, so that's going to use this ratio that we have up above right here. So if I wanted to solve for this length y, what I need to do then is understand that a 22-degree angle has a slope ratio of 2/5, and that's going to be equivalent to y over 25. Those have to be the same. Those are similar triangles. That ratio stays constant. So again, just like we did in the previous problem, we can cross multiply and we end up getting 50 equals 5y. And then I solve for y by dividing on 5 on both sides and get y equals 10. And so why don't you take a moment, pause the video, try and use those ratios that we established yesterday, and we'll come back and we'll highlight some of the key ideas. Let's take a look at how we did. On this first one, this was an 11-degree slope angle. So the ratio of change in y over change in x was 1/5. That's the fact that we established the other day and written above. So I set up that proportion, which is equivalent to 100 over x, change in y over change in x, so you get x equals 500. Moving on to letter C. You should notice that this is a 45-degree angle, and if we have a 45-degree angle, we know that the change in y over the change in x is 1. Well, if this side length here is 13, that means this one also has to be 13, because 13 over 13 will yield 1. So that means A has to be 13. Letter D kind of goes backwards on that. Here we're given the two side lengths are the same. So what kind of a triangle does that have to have, or what kind of a slope angle? Well, that has to be a 45-degree angle. As a reminder, this is pronounced theta, th, theta. It's a Greek letter. It represents the variable for an angle. And so instead of using x or y, we refer to Greek letters in that instance. So that would have to be a 45-degree angle. As I move down to this bottom one, again, I don't have the angle in this instance, so I'm determining the angle measurement. I should recognize that the change in y over the change in x in this case is 2/5. Well, that's a ratio that we're familiar with. That goes all the way back up to here. 2/5 was a 22-degree slope angle. So that means that this angle, although the side lengths are 20 over 50, that ratio is constant if you simplify it to be 2/5. Therefore, that angle has to be 22 degrees. And then lastly, over here, this triangle might have thrown some people for a loop. But what we can recognize is that if this angle down here is 79, that means that this one has to be 11. Our triangle sum theorem tells us that that has to be 11. So instead of being 1 over 5 for the slope ratio, this triangle has kind of been flipped, if you will. So that slope ratio of an 11-degree angle would be 5 over 1. So therefore, y over 7 corresponds to 5 over 1. And if I cross multiply, I get y equals 35. In problem 14, what we're going to do is just reiterate what we did in part F. What I want you to recognize is that 11 degrees and 79 degrees, that those angles are complementary with one another. So remember, complementary angles are angles that add up to 90 degrees. And so complementary angles have a specific relationship when it comes to slope ratios. So complementary angles have reciprocal, if I can spell that correctly, reciprocal slope ratios. And so that was established in the previous problem on letter F. And just to exemplify what I mean by that, we know that an 11-degree angle has a slope ratio of 1/5. Well, if I were to flip that, I would know that a 79-degree angle, and these are, remember, these are complementary angles as they add up to 90 degrees. A 79-degree angle has a slope ratio of 5 over 1. which is evident here in this problem is what we did yesterday, or in the previous slide as well. So complementary angles have reciprocal slope ratios, meaning that if I know an 11-degree angle, then I can also know the slope ratio for a 79-degree angle as I just take the reciprocal of the one that I know. So in practical application into this problem, for the last problem that we're going to do today, if I know that this angle down here is 68 degrees, I can determine the measurement of the other angle that's found within that triangle, which would be this one up here. That angle would have to be 22 degrees because that's complementary with 68, and those three angles here, here, and here all add up to 90. So I know that the slope ratio for a 22-degree angle is 2/5. So 68 degrees is complementary with that. Those add up to 90. So per the last problem, I know that the slope ratio of a 68-degree angle would be 5/2, or the reciprocal of its complement. So with that being said, I can determine this measurement x right here. I know that 68 degrees has a slope ratio of 5/2. And so therefore I know that 5/2, that ratio has to be equivalent to the change in y over the change in x of this triangle, which would be 30/x. So if I cross multiply and solve here, I'm going to get 5x equals 60. And so therefore, when I go to solve this problem, what I'm going to do is I'm going to find out then, dividing by 5, that x would be equal to 12. So now we've kind of expanded our own horizons in terms of understanding that we also don't just have a slope ratio for 11 degrees, which we know is 1/5. We also know then 79 degrees, that ratio would be 5/1, because we know those are complements. We also established that 22 degrees and 68 degrees, those are complements with one another, so 2/5 and 5/2. The reciprocal of a 45-degree slope angle, well, that's just 1, as when you flip 1/1, that still yields just 1. So we're going to go to the math notes on the last slide, and that'll wrap her up for today. This again just re-emphasizes what we just talked about. It says in lesson 4.1.1, you discovered certain slope angles produce slope triangles with special ratios. Below are the triangles you've studied so far. And these are 3 or 4 triangles rather that I would put in my notes to be able to use for later reference. I hope this has been a somewhat useful video for you. Again, if you have questions, feel free to swing by the office hours anytime from 11 to noon. Hope you all stay safe, stay healthy.